Okay, today we're going to talk about AC circuit theory again. We've already worked it out just by plugging in omega and solving the equations with complex numbers, much as we did in the DC case where we only had resistors and real numbers. But today what we're going to do is take a different look at this, go back to our knowledge of passive filtering, and see if we can't use that information to help us understand how the AC circuits are working. Let's review passive circuits. Recall that a passive circuit is a circuit that has only independent sources, either independent voltage sources and or independent current sources, along with resistors, inductors, and capacitors. An active circuit, on the other hand, is a circuit that has at least one amplifier element. This amplifier element could be a transistor, although vacuum tubes are still sometimes used, particularly in some audio applications. And of course, remember that operational amplifiers are built by combinations of transistors. An amplifier element is defined as some kind of circuit element that can control a current, either using a control current or a control voltage. The fundamental of electrical and computer engineering says, if the driving force to a linear circuit is of the form x of t is equal to a sine of 2 pi ft plus theta, then the output will be a times the magnitude of h at that frequency j 2 pi f times sine 2 pi ft plus theta plus the angle of h at j 2 pi f. This is exactly what we were doing when we were reading off the graphs. And of course, h is the frequency response of our circuit. A corollary to this fundamental theorem is something that was done by Fourier. And Fourier showed that any signal x can be written as a linear combination of sinusoids. When we write a signal in this way, we call this representation the Fourier transform. So, the frequency response, through the fundamental theorem of electrical and computer engineering, is a critical characteristic of every circuit. Let's consider the circuit shown. This is a passive filter. We have a source that is in Thevenin form that consists of an independent voltage source, V sub t of t, and a purely resistive impedance, R of t. We then add a load of a capacitor. If we write the equation for this circuit, we have minus V plus I sub C R of t plus I sub C times 1 over SC is equal to 0. Solving that equation for I sub C, we get I sub C of S is equal to V sub t of S over R sub t plus 1 over SC. We can look at the voltage across that capacitor, Vc of t, or in the S domain, Vc of S, will be equal to 1 over Sc times the current through the capacitor, I sub C of S. So, from this we can write I sub C of S is equal to Sc V sub C of S, and substituting this result back into the very first relationship, we have IC of S is equal to SC VC of S, which is equal to the right-hand side, V sub t over R sub t plus 1 over SC. Dividing through by SC and also VT, we end up with the ratio VC over VT is equal to 1 over SC times the quantity RT plus 1 over SC. Multiplying through by on the denominator by SC, we get 1 over SCRT plus 1. And if we consider this, we look at what happens where S approaches 0, which corresponds to omega is equal to 0. We end up with a constant. And if we look at what happens as omega approaches infinity, we end up with 1 over infinity, which approaches 0. So this is a low-pass filter. If we want to look at the frequency response, we can plug in j omega for S. So h of s was equal to 1 over s times CRT plus 1. If we substitute j omega for s, we end up with this equation. We can rewrite the equation in a form that provides some physical insight into the circuit. We end up with, and by using Euler's identity, 1 over square root of 1 plus omega squared c squared r sub t squared times e to the minus j inverse tangent of omega CRT. We can call 1 over RTC, we'll just call omega naught, and then we can rewrite the equation as h of j omega is equal to 1 over the square root of 1 plus omega over omega naught squared times e to the minus j inverse tangent of omega over omega naught. Now let's see what happens when we use a particular voltage source. Suppose our voltage source is V of t is equal to 10 cosine t, 10t. So our amplitude is 10 and our value of omega is 10 radians per second. Perhaps we want to know what the value is of V sub c of t when the capacitor is 1 farad and the resistance RT is 2 ohms. We don't need to rewrite the equations, but we can just plug into our previous equation. I sub c is equal to 10 over 2 plus 1 over j times 10. And this is, of course, a real number of our complex number. You can just use complex division on your calculator and you solve. You get 4.9938 at an angle of 2.86 degrees. Please be careful not to round this to 5 because that totally neglects the effect of the capacitor. So, we can then take this phasor notation and write it in time domain. I sub c of t is equal to the amplitude 4.9938 cosine of omega t. Remember, omega is 10 radians per second, plus the angle, which is 2.86 degrees, and the unit, of course, is amps. Using the generalized Ohm's law, we know that V sub c is equal to I sub c times 1 over SC, and 1 over SC is going to be 1 over J times 10. So we can divide the phasor for IC by the phasor corresponding to J10. Realize, of course, that this is 10 at an angle of 90 degrees. You can remember this easily if you remember how to plot complex numbers. So we divide the magnitude by the magnitude and we get 0.49938 and subtract the denominator angle from the numerator angle and get an angle of minus 87.14 degrees. Writing that in time domain, we can get 0.49938 cosine of omega t, again 10 radians per second, minus that angle, or plus that angle, which is minus 87.14 degrees, and the unit is volts. Now, think back to what we did when we looked at our frequency response. Remember that we found the frequency response h of j omega is equal to this. Plugging in the values for RT and CT, we can and omega, we can solve this form. We end up with a value of h of j times 10. Okay, so to figure out what VC will be, we recall that h is equal to VC over VT, okay, the output voltage over the input voltage, as we defined it. So we can then figure out VC by multiplying the input voltage, which was 10 at an angle of 0 degrees, times the transfer function h at j times 10. When we do this multiplication, we multiply 10 by 0.049938 to get 0.49938. And of course, we add the angles since we're multiplying. 0 plus minus 87.1376 is minus 87.1376. 1376. If you want to keep the full precision. Okay. So we can write then in the time domain VC of t is equal to the amplitude 0.49938 cosine of omega t, remember omega is 10 radians per second for our case, plus the angle, which is minus 87.1376 degrees. Okay, and this is the same exact result that we saw when we did AC analysis on this circuit. Let's consider another example. This circuit's quite a bit more complicated. We have an independent voltage source Vn. Of course, it is a function of time, even though I don't show that. We have 3 resistors and a capacitor, and we're going to define our output voltage across that capacitor. So we need to ask ourselves, what is V out of t when Vn of t is equal to minus sine of 1000 t volts? Notice that the Vn is given as a sine rather than a cosine, so we will need to account for this in the angle when we look at the phasors later. Writing the KCL equations for this circuit, we're going to define this point as V minus Vn over 2000 plus V minus 0 over 2000 plus V minus V out over 1000 is equal to 0. That will be the first equation. The second equation will have V out minus V over 1000 plus V out minus 0 over 1 over SC, where C is 10 microfarads, and that gives us this equation. Be sure that you remember to write 1 over SC in the denominator. Sometimes people forget that. Okay, now we have 2 equations, 3 unknowns, but remember we're solving as the transfer function like we did with the passive circuit case. So what we're going to be solving for is V out over V in. So we have basically, this will be one of our unknowns and V will be one of our unknowns. So 3 unknowns, but we're going to treat one of them as a ratio. So when we solve that, we end up with V out times 1.01 S is equal to V. So all we did there was we took this second equation, flipped this term over here, and solved for V out and V. We could then substitute that into the first equation. Okay, so we'll take the first equation. We will simplify it quite a bit. Okay, substitute this first equation into the second equation, and we solve, and we get 1 plus 0.2 times V out is equal to 1/2 times V in. Solve for V out over V in, and we will end up with the transfer function 1 over the quantity 2 plus 0.04 S. And so that's our transfer function. This is exactly what we did when we were analyzing passive circuits. So now, using the fundamental theorem of electrical and computer engineering, we are going to plug in our particular frequency of interest. Let's go back and recall. We were looking at minus 5 sine of 1000 t, which in phasors is 5 at an angle of 90 degrees. We will plug in 1000 for omega. When we take our h of s, substitute 1000 for omega, we will get 1 over a complex number, which is simple division. You could do that with your calculator, of course, and then you end up with 0.025 at an angle of minus 87.1376 degrees. So that is the transfer function at omega is equal to 1000 radians per second. So to find out what V out is, we take that transfer function, which is now a complex number, and multiply it by our input. To multiply these values, we take 5 times, we multiply the magnitudes to get 0.1248, and we add the angles. 90 plus minus 87.1376 will give us an angle of 2.8624 degrees. Please be sure not to round a lot at your in-between steps. In fact, it's best to store these interim values in your calculator. You're not finished until you take your phasor representation and write it as a time domain signal. So we know that V out of t is going to be the amplitude 0.1248 cosine omega t plus the angle 2.8624 degrees, and the unit is volts. If we wanted to use AC analysis, we could just take our two equations, okay, substitute in the input as a phasor, substitute in j omega, and then solve for V out. Basically, we can write this in matrix form. We write these two equations in matrix form, and we'll end up with this. You can plug it into your calculator. Not every calculator will solve some systems of complex equations, so please be aware of what your calculator can do. MATLAB can solve this, of course. And when we solve for V out, we end up with 0.1248 as the magnitude, and the angle is 2.8624. So this is the time domain signal, 0.1248 cosine omega is 1,000 radians per second times t plus the angle 2.8624 degrees, and the unit is volts. This is the same result you get using the transfer function. So which approach should you use? It doesn't matter. If you have already been asked to calculate the transfer function, it is usually simpler just to go ahead and use that transfer function you've already calculated. But if you have not, if I don't ask you a question that asks you to calculate the transfer function, it's just as simple to plug in the complex values and solve without using the transfer function. So this is up to you, and it might depend on the circumstances. Let's look at the MATLAB we used to solve that system of equations. So here's the system of equations. We have 4 over 2,000 minus 1 over 1,000 minus 1 over 1,000, and then 1 over 1,000 plus 0.01 j. That is going to be our matrix A. Notice that when you're using MATLAB, it's just as easy to plug in the calculations you need to make. That will help keep your internal, it'll carry around your intermediate values very nicely. Okay, for B, we have 5 at an angle of 90 over 2,000 and 0. 5 at an angle of 90 over 2,000. 5 at an angle of 90 is just j times 5, or 5j, and we divide by 2,000. There's many ways you could type this into MATLAB, but any of the valid forms work. Of course, since this is a column vector, we have a semicolon in between the two rows. Then to determine the values, we use the backslash operator. So V is equal to A backslash B. That solves for V, which is our output vector. Okay, and we can find the magnitude of V by using the ABS function, and then we just have to remember which of the values we cared about. Let's go back. We were solving for V and V out. So the first one is V and the second one's V out. So we cared about 0.1248. To get the angle of the output, we do angle V. That gives me the angle of radians. So to convert it to degrees, we multiply by 180 over pi. And that gives me the angle. Remember, the first one is for V, the second one's for V out. The second one is the one we care to solve for. So MATLAB can be a very valuable tool for checking your answers. So in summary, we've looked at AC analysis in two different ways. We've used our knowledge of transfer functions from our passive filtering analysis section of our course, and then substituted in the value for j omega for S. Okay. We've also done AC analysis where we solve the equations and simply use the complex numbers. We have seen today that AC analysis is just a special case of the transfer function approach. This makes it much easier to understand what's going on if we have a good understanding of how transfer functions work. And last, I discussed how you can use MATLAB to do these computations. Thanks for watching. I hope you found this helpful.